Hello, and welcome to Lesson 10 of this Introduction to Probability of Wolfram U. The topic for this lesson is Properties of Random Variables. Let's begin. Human perception is a mix of sensory stimulus and prior knowledge, which leads to direct and constructivist theories of perception, respectively. When we see the shape of a doll, we expect the doll to have a face. When we see a sprout, we expect a future greater plant. Random variables are useful mathematical tools, but they're a bit mysterious, so in an attempt to demystify them, we use a central concept, expectation. In this lesson, you'll learn about different properties of random variables, and expectation itself, to know how to compute different metrics that inform your perception on any random variable, starting with the most common metric, the mean, or average, which is the expected value of a random variable. This Greek letter, called mu, is a standard variable for mean. Formally, the mean is the expectation of x, the sum of x times the probability for the discrete case, and the integral of x times the probability for the continuous case. For example, the weight of customer service follows a PDF 2e power minus 2x. We can just build the distribution for it. The Wolfram language both has the mean and expectation functions, so we can use the expectation and the mean to get the mean of the distribution. The second most important metric is the variance, which is the squared expected variation. We also have the sister concept, the standard deviation, which is the expected variation. A small variance means most values are close to the average, whereas a large variance means that a lot more values are far from the average. Since sigma is the standard symbol for standard deviation, sigma squared is the standard symbol for variance. Formally, the variance is the expectation of x minus the mean power 2. As a small demonstration, using our example, computing the expectation of x minus the mean power 2 and taking the variance is the same value. And the standard deviation is indeed the root of the variance. Expectation has many useful properties for algebraic manipulation. Constants added or multiplied to a variable can get outside the expectation. The expectation of adding two variables is equivalent to adding their expectations, and this actually can be extended to any number of variables. For example, if the previous distribution was the call center and after that, the time to reach the technical help was distributed by the PDF e power minus x, what would be the expected wait time? Well, just create a new probability distribution for technical help and find the expectation of adding two variables. And that is indeed equivalent to adding their expectations. What if you want the variance of a sum of random variables? This is where things get complicated. You see, if you deal with independent variables, then you can still add variances, and the variance of a sum of random variables is the sum of their variances, just like expectation. But what happens when the random variables are dependent, meaning the probability of one affects the probability of the other? Well, there is a formula for that, but it's more complicated. The variance of a sum of random variables is the sum of their variances plus twice the sum of their covariances. But wait, what even is covariance? Covariance is a measure of relationship between two random variables. It's defined as the expectation of the first random variable minus its mean times the second random variable minus its mean. The property of independent variables being different can be explained by the fact expectation allows us to isolate independent variables like this. Let's cover a few properties of covariance, so you get an intuition. The covariance of independent events is 0. The covariance of xy is the same as the covariance of yx. The variance is a special case of the covariance when you take twice the same variable. And constant factors can be isolated like this. Positive covariance indicates proportional growth, and negative covariance indicates inverse proportional growth. Depending on the context, you may interpret one unit change of x resulting in the covariance change in y, but this depends on the context. Interpreting the covariance is often difficult, especially if you just want to know the strength of the relationship between two random variables. So while covariance interpretation is dependent on variables, correlation interpretation is standardized. Correlation solves the issue by being the standardized degree to which two or more quantities are linearly associated, mathematically defined as the covariance xy divided by the standard deviation of x and y. Now that you've removed the variability of each variable, you can easily get some understanding. Namely, the correlation goes from -1 to 1, 1 meaning both variables increase together, -1 meaning as one increases, the other decreases. And like covariance, 0 means that they're independent. You can generalize the idea of average to moments. The mean is the expectation of x, or x power 1. So what if you calculate a higher power? The nth moment of a random variable is defined as the expectation of x power n. But why do we want to do that? Why use moments? Well, they have two purposes. First, whenever you're calculating by hand some expectation, knowing the moment can help simplify algebraically the expectation. But most importantly, they help define most properties of random variables. Okay, let's start. The first moment is the same as the mean, as you can see. Then the second characteristic is the variance, which characterizes dispersion. It's calculated as the second moment minus the first power 2, or just the variance function. The third characteristic is the skewness, which characterizes the asymmetry of the distribution. It's calculated as the third moment divided by the second moment power 3 on 2, or the skewness function. Finally, the fourth characteristic is the kurtosis, which characterizes the concentration of data around the peak and tails of the distribution. It's calculated as the fourth moment divided by the second moment power 2, or the kurtosis function. If you've ever computed a moment, you know it's far from trivial, as sums and integrations can get really complicated. Fortunately, some distributions have moment-generating functions, defined as the expectation of e power tx. Okay, let's say you have a moment-generating function. How do you even generate moments? How do you generate the nth moment? Well, just differentiate the generating function n times, then find the limit at t to 0. For example, let's say you have your moment-generating function. Then you can generate the first moment by deriving once, then taking the limit at 0. And since it's the first moment, comparing it to the mean, you get the same answer. Wow, so many properties. You know so much about random variables already. Just from expectation. What's so magical about expectation anyway? Why is the summation or integration of multiplying a function by a probability magically solving all these problems? Well, advanced statistics and probability will often talk about predictors, which are functions attempting to predict the behavior of a random variable in some way. There's a cool theorem about that answers most of these questions, and it's called, usually, the conditional expectation. Consider two random variables, x and y. Your task is to estimate y only using the variable x. Well, you'd have to invent some kind of function of x which estimates y well. So let's call that function g of x. Then the expectation of y minus g of x squared, that is, the error, is greater or equal to the expectation of y minus the expectation of y considering x all squared. That is, the error of the expectation. In other words, the expectation is actually always the best predictor. So in this lesson, you learned about different properties of random variables. You also saw useful algebraic properties of expectation. Most significantly, the expectation of sums and the variance of sums. You should now be able to compute and interpret mean, variance, skewness, kurtosis, covariance, correlation, moments, and you'd be able to use the moment generating function. This lesson helped you to get an understanding of random variables through theory. But the next lesson will complete your understanding practically.